Let's talk about how we developed the last two of our kinematics equations. And these are actually just going to be developed from the definition of average velocity and average acceleration. So here we go. To remind you, what is average velocity? That's simply the displacement over the time, or change in position over time, which would lead us simply to x final minus x initial, that quantity divided by the time, which gives us that super fantastic first equation on our equation sheet for the constant or average velocity, where the final position is equal to the initial position plus the average velocity or constant velocity times time. In math, we learned that we can take an average simply by adding up all the different terms and then dividing by the total number of terms. So that means that our average velocity could also be written as v initial plus v final, that quantity divided by 2. Now, if we combine those two ideas, we can replace the average velocity in our kinematics equation with our two different velocities, our initial and final velocity, as defined by the average velocity from math, leading us to the equation that you see here, which can be rearranged to the super convenient version of x final is equal to x initial plus 1/2 the quantity v initial plus v final times time. So we're going to use that equation and combine it with the definition of acceleration to get our last two kinematics equations. So here's our two equations that we're going to use. Remember, our v final equals v initial plus at is just that convenient rearrangement of the definition of acceleration. So the first way we're going to do this is by using the definition of acceleration to basically replace the final velocity in our equation over here. So let's do that. We're going to go replace out our final velocity so that it becomes x final is x initial plus 1/2 the quantity v initial plus the quantity v initial plus acceleration times time, that whole quantity multiplied by time. No one thinks that this is a nice convenient arrangement. It is ugly as sin. So let's simplify this a little bit more. And that's going to simplify down to give us the awesome final equation, x final is equal to x initial plus v initial t plus 1/2 at squared. So that's our first fantastic position as a function of time for when the object is accelerating equation. Now, the other thing we want to do is, if you notice through all of our equations, time is everywhere. It would be fantastic to have a non-time version. So we're going to take these two equations and rearrange them a little bit differently, this time eliminating time. So by doing these rearrangements, we can now replace the time in our first equation in order to get that x final is equal to x initial plus 1/2 the quantity v initial plus v final, that quantity multiplied by the quantity of v final minus v initial over the acceleration. Again, no one thinks this is convenient or easy or anything else. It's also one that no one would expect you to know how to do or what algebraic steps you're going to take next. I know what the final equation is supposed to look like, so I'm going to do that for you. Again, this is more about following the process so you see that these equations don't pop out of nowhere. So what I'm going to start by is pulling all of my denominators together, and I'm basically out of room, so I'm going to go to a new slide. After, of course, I FOIL out that quantity of v initial plus v final times the quantity v final minus v initial, which is just the difference of squares. You can check that on your calculator or do out all of the algebra if you want. Wouldn't bother. So finally got to our new slide, and we're going to keep going here. Again, this is a ton of ugly algebra, and the only reason I'm nowhere to go is because I know what we're trying to do is isolate and solve for our fantastic, and if you remember me, I like to know what I'm solving for, so we're going to be solving for that in final velocity squared. So first things first, we're going to subtract the initial position from both sides. Then to continue, we're trying to get v final squared by itself. So we're going to multiply both sides by 2a. Okay. And then we can move v initial squared to the opposite side by adding it to both sides, which will give us our final equation that v final squared is equal to v initial squared plus 2a times the quantity x final minus x initial, also known as the displacement. And so we now have developed all of our equations. Thanks.